So look, I used to swim competitively and I absolutely hated it. I remember that at the end of every single lap, my coach Rod would tell me, Nick, rotate your shoulders. Nick, don't look up. Nick, make your arms straight. In my mind, I'm like, my arm's straight. How much straighter do you want it to be, Rod? Now, if only I had the tech that we're about to take a look at in this video, this would have made my life probably about 1 billion times easier, and I probably would have actually paid attention during swimming. So what is it that we're going to be taking a look at in this video? Well, we're going to be taking a look at a technique called multi-person pose estimation. This is a technique that allows you to detect key points around your body. So it would be able to detect my wrist, my elbow, and my shoulder to be able to tell Rod that, hey, my arm's hella straight, bruh. In this particular case, there's a whole bunch of different use cases around this, but one of the principal ones is kinematics, which is the analysis of the body and all of the different angles and joints within a body. So that's exactly what we're going to be taking a look at. What's happening, guys? My name is Nicholas Renard, and in this video, we're going to be taking a look at Google's new multi-person pose estimation model built on top of the Movenet Lightning model. Now, the great thing about this model is that it is hella fast. It is designed specifically for sports and exercise-based applications, and it's ideally designed for being around about 3 to 6 feet away from your camera. So if you're thinking about doing stuff which is super far out in the distance, this might not necessarily be the model for you. That being said, there are a whole bunch of different applications where this could come into play. Say, for example, you wanted to analyze your swim stroke, or you had a team of golfers that was teeing off at a particular tee. You could actually analyze all of their strokes in real time because it is a multi-person model. You had a classroom full of people doing yoga. Again, this is probably the model that you would want to take a look at. Now, whilst there isn't a dedicated paper for this model, the model card from Tensorflow Hub tells us that it's comprised of 3 famous models. The backbone network is built using a Mobilenet V2 model. The feature extraction layer is composed of a feature pyramid network. And last but not least, the layer that outputs the key points, aka prediction heads, is comprised of a CentiNet model. Now, I'll link to all of these papers in the description below. Let's take a look as to what we'll be going through. So in this video, we're going to start out by going and installing the multi-person Movenet model. Now, specifically, in order to do that, we're going to need TensorFlow and TensorFlow Hub. And as per usual, we're going to take this all step by step so you can see how to walk through and do it. Then what we're going to do is we're going to make detections using a video, but also our webcam. So we'll actually use some pre-existing videos so you can see how this performs with multiple people in the frame. And then what we're going to do is we're going to leverage some of the code that we wrote in the previous Movenet tutorial to be able to draw the key points and the edges. But again, as per usual, all the code is going to be available in the description below. Let's take a deeper look as to how it's all going to work. So as I was saying, what we're first up going to do is we're going to install TensorFlow and TensorFlow Hub. So TensorFlow Hub is going to allow us to pre-download the existing model, so you don't need to go and separately download stuff. It's just all going to work. Then we'll load our multi-person Movenet Lightning model into our Jupyter notebook so we're able to actually use it. And then we're going to make some detections using our webcam, and we'll also use an existing video. So I've got a couple of videos that we'll actually be able to test it out. But if you wanted to use your own video, you could do that super easily. Ready to do it? Let's get to it. Alrighty, guys. So let's kick this thing off. So in this tutorial, there's going to be roughly 5 things that we need to do in order to get this thing up and off the ground. So first up, what we're going to need to do is install and import our dependencies. So our key dependencies, I think, are going to be TensorFlow, TensorFlow Hub, and OpenCV. And I'll explain when and where we're going to be using those as we get to them. Then we're going to load up our model. Now, the cool thing about loading up this model is that we're able to use TensorFlow Hub. So TensorFlow Hub is a place where there's a whole bunch of existing repositories that you can go on ahead and use. So this is really, really cool if you have specific machine learning or deep learning problems that you want to solve and you want to leverage a pre-existing model. It's really cool. There's a whole bunch of stuff available here. Then we're going to make detections, and we're going to do detections 2 ways. So we're going to master chef it up in here. So we'll make some detections using a webcam. So the webcam that I'm currently looking at the moment, well, I've got one right next to it. And we're also going to do it using a pre-existing video. So say, for example, you've gone and recorded yourself with your iPhone and you wanted to make, or your phone, whatever in general, and you wanted to go and perform this multi-pose tracking using that video, you can actually do that relatively easily. It's a single line of code that you need to change. Not even a single line, it's a single value. Then we're going to also draw our key points and draw our edges. So these are the two, I guess, the two key things that you really want to see when you're actually building this up. So what we're going to do for those is we're just going to leverage the existing drawing methodologies that we used in the previous Movenet tutorial, and I'll link to that somewhere up above so you can do that as well. Cool. All right, that's enough of me blabbing. Let's go on ahead and install some stuff. So first up, what we're going to do is we're going to install our key dependencies. Alrighty, those are our dependencies installed. So I went and wrote one line of code there. And specifically what we've gone and written is pip install TensorFlow equals 2.4.1, TensorFlow -GPU equals 2.4.1, TensorFlow -hub, OpenCV Python, and Matplotlib. Now let's explain what each one of these are going to be used for. So these two lines here are installing TensorFlow, and we're specifically installing TensorFlow with a GPU in this particular case, and we're installing the version 2.4.1. Now, if you're going to be using your GPU in this particular case, you want to make sure that you've got a matching CUDA version. So if you don't know how to do that, I'll link to the tutorial where I show how to do that below. But in this particular case, I've already got CUDA installed, so this is going to allow us to leverage GPU acceleration. Then we've gone and installed TensorFlow Hub. So TensorFlow Hub is going to be what allows us to load up our Movenet model. Now, the model that we're specifically going to be using, if we go on ahead and zoom into that search bar, is Movenet. I believe it's multi-person. Let's see if that gives us any results. Oh, Movenet. What is it? Multi-pose. So you can see that there. So I've just typed in Movenet, and then you can see Movenet /multi-pose /lightning. So this is going to be the model that we want to use. Now, I always get asked for the actual paper that represents this model. There isn't an explicit paper for this particular model, but what there is this model card. So if you wanted to see how this specific model is being built, you can actually open up that model card, and it's going to give you a bunch of information about this model. Now, in the intro, I did mention a little bit about the architecture. So you can actually see here that this specific model uses a Mobilenet V2 model as the backbone. It uses a feature pyramid network to extract the different layers, and it uses a CentiNet to compose or predict as the prediction heads. So the Mobilenet V2 model is an existing image-based classification model, I believe, or typically used for image classification and object detection. Feature pyramid network is all about extracting different features at different layers or different scales of images. And our CentiNet model is actually what gives us the key points. So you'll see that a little bit later. Now, what you're actually going to get out of this model is it actually has a maximum of 6 people it can detect. So you can see that over there. So you can see it says 6 people in the image frame simultaneously, and you're actually going to get 17 key points per person. So it's actually going to, the list is actually here. So you can see it's going to extract nose, left eye, left ear, right ear, left shoulder, left elbow, right elbow, left wrist, left hip, left knee, left ankle, right ankle. So all of these are going to be the key points that you're actually able to extract using this specific model. Now, it does have a couple of extras. So if you scroll on down, it actually draws a bounding box around, or it actually gives you the coordinates for a bounding box as well. So the last 5 values in the results array, and I'll show you these as well, are going to be the Y minimum, X minimum, Y max, X max. So if you've seen my object detection tutorials, these values allow us to go and draw a bounding box around ourselves if we wanted to. And you can see it basically says there, they represent the region of the bounding box in normalized coordinates. So when it says normalized coordinates, what that means is that you need to scale it to the size of your image, which we'll handle in our code anyway. So that's a little bit about the actual model that we're going to be using. And again, I'll include links to all of this stuff in the description below so you can take a look. What else did we install? So we installed OpenCV-Python. So this is going to give us OpenCV. So OpenCV is an open source computer vision library that just makes it really easy to work with your webcams and different image-based sources. And then we're going to install Matplotlib. I always install this as a backstop. So if you need to go and render a frame and see if stuff or how stuff actually fits together, this is super useful. Cool. So those are our dependencies now installed. Now what we need to do is import them. So let's go on ahead and do that. Alrighty, those are our dependencies now imported. So we've gone and written 5 different lines of code there. So first up, what we've gone and done is we've imported TensorFlow as TF. So this is going to give us TensorFlow, so the underlying deep learning framework that we need to be able to run our key point model. Then we've gone and imported TensorFlow Hub. So in order to do that, we've written import TensorFlow _ hub as hub. So this means that we're going to be able to refer to it as the variable hub. And remember, hub is going to allow us to load in our Movenet multi-pose lightning model. Then we've imported CV2. So this is just the naming of OpenCV. So import CV2 gives us OpenCV. And you'll see that a little bit later. We've then gone and imported Matplotlib. So from Matplotlib, import pyplot as PLT. So this means we'll be able to refer to pyplot as PLT. So if you wanted to go and render stuff, you can type plot.imshow. Really useful function, which allows you to go and render an image. And then we've imported NumPy. So import NumPy as NP. So NumPy is going to be used mainly in step 3 and step 4 to go and draw our key points and draw our edges. But once we get to that section, we're actually going to be leveraging the code that we wrote in the existing Movenet Lightning model. But again, all of it will be available in the description below, so you'll be able to pick that up. Cool. All right, so 5 lines of code. So TensorFlow, TensorFlow Hub, OpenCV, Matplotlib, and NumPy. Now, before we go any further, if you are using a GPU, what you want to do is you want to ensure that you limit the memory growth. Otherwise, it will just throw out of memory errors. So this is purely optional. So I'm just going to add a comment, optional if you are using a GPU. By adding this line of code, this means that you're able to scale up the images that you pass through to the Movenet model without throwing out of memory errors. So it's basically going to hold TensorFlow to consuming absolutely all of your VRAM on your machine. So let's go on ahead and add this. Okay, so that is our memory growth limit set. So let's go and take a look at what we wrote there. So we wrote 3 different lines of code. And remember, this is purely optional if you're using a GPU. So I've written GPUs equals tf.config.experimental.list_physical_devices. So this is going to list out all the GPUs that we've actually got. So if I print out GPUs, you can see that I've only got 1 on this machine. I've got a 2070 Super. So if you're using another GPU, it should ideally, or if you've got multiple GPUs, you'll see multiple devices down here. So I've written GPUs equals tf.config.experimental.list_physical_devices. And then I've passed through that I want to return only my GPUs. So inside of that, we've passed through a string variable called GPU. Then what we're doing is we're looping through each one of our GPUs inside of here. So if we wanted to grab a single GPU, we could definitely do that. So for GPU and GPUs, tf.config.experimental.set_memory_growth. And then we're passing through the individual GPU at that time, and we're setting that we want our memory growth to be limited equal to true. So this basically means that you're not going to get these out of memory errors. So when I was actually testing this, when I scaled up the image that I passed through to the Movenet Lightning model, I would get out of memory errors. So by doing this, you're not going to hit that stopping error, right? Cool. So 3 lines to be able to limit your memory growth. So we can delete this line down here. Okay, so that is step 0 now done. So we've now imported and installed our dependencies, and we've also gone and set our memory growth limit. Now what we can go on ahead and do is load up our model. So let's do it. Alrighty, that is our model loaded. So what I've gone and written there is model equals hub, or we've gone and written 2 lines of code there. The first line is model equals hub.load, and this is specifically going and grabbing our multi-pose model from TensorFlow Hub. So remember, we can go and download this. So it's basically using this link over here to go and download that model. Now, the full line is model equals hub.load, and then https://tfhub.dev/google/movenet/multipose/lightning/1. Then what we're actually doing is we're extracting the model itself. So I've written Movenet equals model.signatures, and then we're grabbing the default model. So in order to do that, we've used some string indexing. So I've passed through inside of square brackets, serving underscore default. Now these two lines of code are pretty much out of the baseline tutorial. So if you actually go and take a look, it's actually these two lines of code there. So they're exactly as specified in the documentation. So the first one is going and downloading the model. The second one is actually going and setting up a new variable so we can actually go and use that model. So 2 lines of code to be able to go and load our model. Now that that's done, what we can actually go on ahead and do is start making some detections. Now, first up, what we'll do is we'll probably make some detections with our webcam. Let's give ourselves some more space. And then I've also got a bunch of videos that we can test this out with as well. So if you wanted to use it on pre-existing videos, you could definitely do that. So first up, let's go on ahead and access our webcam, make sure we can do that. Okay, so this is pretty much our standard webcam capture code. So we've written this a bunch of times in previous computer vision tutorials. If you wanted a deeper breakdown, by all means, go and take a look at those, but I'll quickly walk through each one of these lines. So first up, what we've gone and written is cap equals cv2.video capture. So this establishes a connection to our webcam. Then the next line is checking to make sure that the capture is still open. So while cap.isOpen, and then I've included a set of parentheses and then a colon. Actually, key thing to note is that this value here may change. So if you've got a number of different video capture devices, then you might need to test out which specific device actually needs to be passed through. So previously, this used to be video capture, or the main video capture device on my Windows machine used to be video capture device 0. Now, because I've gone and installed some new stuff, I believe it's 2, but we'll test it out and see. So this establishes the connection, this checks it's still open, and then think of a video feed as a number of frames. So what we're going to do is we're going to read the current frame that the video is at using cap.read, and we're going to unpack the results we get from that. So we'll get a return value and we'll also get the frame. The frame is actually the image that you want. So the frame is going to be what we pass through to our Movenet model in a second. Then what I've gone and done is I've written cv2.imshow. So this actually renders the image to the screen. And to that, we've passed through 2 values, so 2 positional arguments. So first up, we pass through what we want our frame to be named. In this case, Movenet multipose. So you'll see at the top of the frame, that's what it's actually called. And then we're actually passing through the frame. So what we've got from over here. Then I've gone and written, so everything from down here downwards is all to do with what do we do when we want to exit. Now, specifically, the way that we are going to exit this frame is by hitting Q on our keyboard. So what we do is we wait for a key to be pressed. So if cv2.wait key, and then we're checking every 10 milliseconds, and the key that we press is Q, so 0xff, so that's our key, equals odd or equals odd Q. So this is looking for the key Q. So if you wanted to change the key that's pressed, you can just change that value there to the key that you want to detect or look for. And if that condition is met, then what we're going to do is break out of this loop. Because remember, we've got a while loop, so we're going to break out of it here if we hit Q on our keyboard. Then assuming that happens, once we break out of the loop, we're going to run cap.release, which is going to release our webcam. And then we're going to run cv2.destroy all windows, and this is going to close stuff down. So if we run this, hopefully we should be able to get a webcam feed, and you'll get a little pop-up towards the bottom of your screen. So let's wait and see if that works. So that does not look like it's worked. So we might need to try a different video capture device. So let's try 3. Okay, cool. So that is working, although it is very small. Kind of weird. We gone and changed our frame size. I don't know what was going on there, but if I go back to webcam device 3, it looks like it's opening back up successfully now. So the weird thing about that was that it was a tiny little square before, whereas I know the resolution should be about what is it? So 480 by 640 wide. So you can see that that is now working. So again, you might need to play around with the specific webcam device that you're going to use. But in this case, you can see that that is rendering our webcam successfully. So it was webcam device or it was video capture device 3. Otherwise, you're going to get those weird little errors. And sometimes you might need to shut it down and reopen it if it's not giving you the right resolution. But in this case, we've got our webcam capture device. So what we can now do is we can actually use the frame. So I've just hit Q on my keyboard to close that down. So we can actually access the frame. So let's type in frame. So this is actually the image representation of what we're actually getting from our webcam. So if we actually wanted to see this, I can type plot.imshow. Let's get rid of this bar. So this is Matplotlib rendering it. So you can see that this actually allows us to look at our image. Now it looks a little bit blue because when we go and access our image from OpenCV, it's going to read it in as BGR, but Matplotlib doesn't go in or shift those color channels around. If we wanted to recolor it properly, then we need to just change the color code to RGB. So if we do that quickly, let me show you. So cv2.cvt color. And then pass through our frame, and then we pass through a color conversion code, so cv2.color, it's BGR to RGB, and then close that. So you can see the coloring is now fixed now. So that it's just reordering the color channel, so no biggie there. Alrighty, cool. So now that that is done, the next thing that we actually want to go on ahead and do is make some detections with the Movenet multi-person model. So I'm just going to delete that. We don't need that anymore. So what we're going to do is inside of this loop, we're actually going to take this frame that we've got here and pass it through to our Movenet multi-person model. Now, a key thing to call out is that this model is expecting, I don't know if it says it over here. Yeah, okay, here. This is really, really important. So you need to ensure that you resize the image to be a multiple of 32. And it needs to be roughly 256 pixels wide. So what we're going to do is we're going to grab our frame, we're going to resize it to a multiple of 32, and then what we'll do is we'll pass that to our Movenet model. So let's go on ahead and do this. So inside here, we're going to do that. Okay, that's the first part of our code done. Now, I haven't actually gone and made our detections yet. So I wanted to sort of take this step by step and show you what we're doing first. So first up, what we're doing is we're making a copy of our frame. Now, the reason that we're doing that is because we are going to go and make detections using this resized image, but then we want to render it using the same size of frame. So we're going to make our copy and create that as a variable called image. Then we're going to resize it. So remember, we need to make it a multiple of 32. This is exactly what we're doing here. So we're grabbing, or we're going to set it equal to 256. So 256 divided by 32 is 8, which is a successful multiple. So we could also make a 512, or what is it? 512 plus 256. We could do that as well. We might do that with some of the videos. So we could do that as well. So what's that? 768. You could go larger, but you will reach memory limits as well. So just another thing to keep in mind, and it will also slow down the detections. So the line that we wrote there is img equals tf. So we're going and overriding this variable. So image equals tf.image.resize with pad. So this automatically pads our images with blank zeros if you don't actually, or if you're reshaping to an odd size or a size which doesn't match the aspect ratio of the original image. So that's perfectly cool. So tf.image.resize with pad, and then tf.expand_dims. And then we're passing through our image there to extract or to encapsulate it inside of another array. And then we're passing through comma 256 by 256. Then what I've gone and written is input_image equals tf.cast, and then we're actually converting it to an integer with a 32-bit integer. So we're creating a new variable called input_image, and we're using tf.cast to go and convert that into a different data type. So specifically a 32-bit integer. Then what we can go and do is actually make our detection. So let's remove this. We're not detecting here. Alrighty, so let's start by making our detection. So this is going to be our detection section, and we're initially just going to make a detection and print it out. Because what we'll need to do is we'll need to apply a little bit of data transformation to get our specific key points that we want. So let's go on ahead and do this. So first up, let's make our detections. Okay, so we've just gone and added 2 additional lines of code there. So I've written results equals Movenet, and then to that we're passing through our input image from here, and then we're just going to go on ahead and print our results. So we've written 2 additional lines of code. So this one is actually using the Movenet model from over here, and it's actually accepting our input image as a positional argument, and then we'll print out those results. So let's actually go and run this, and fingers crossed, all things holding equal, we should successfully get a webcam pop up, and we should get some results printed out. Okay, so that's looking pretty good. So we've got our webcam, that's all running, and you can see that we've got this output down here, which is good. All right, so what we can do is hit Q. So right now we're not actually rendering anything, right? But we are getting this output, which is a good sign. So if we go and take a look at our output, we can get rid of this. Wait, what's it called? It's called results. So you can see that we've got all of our output data there. So it's stored inside of what looks like a dictionary. So you can see the squiggly brackets. So what we can do is we can go and grab, let's take a look at what type or what keys we've got. All right, so we've got 1 key. So to grab the result, we can grab output underscore 0. And effectively, let's take a look at a full result. Effectively, what we're going to be doing is grabbing this here. Let me zoom out a little so you can see it a bit better. Right, so it's this big array here. That actually represents one set of detections. Now, what this actually is let me actually explain this to you. So we've got a set of arrays wrapped inside of a single array, and then we've actually got 6 people, so that's that value there. And then we've got 56 key points, or 56 values inside of each result. Now, what those values represent are the Y coordinate, the X coordinate, the, I believe, X, Y, and score. Yeah, score. So X, Y, X, and the score. And then that multiplied by 17 key points should give us, so that's 3 multiplied by 17. So that gives us 51 of those values represent our key points. And then you've got another 5 values. And those last 5 values in each one of these are going to be the bounding box coordinates that we get back from the Movenet model. Cool. So in order to get those results though and get it ready for rendering, what we need to do is a little bit of transformation. So first up, what we need to do is we just want the first 51 values because those represent our actual key points. Now to get our values out of this, we can access this NumPy value here. So to do that, we can type or use some indexing. So to our results variable, we can type output underscore 0, and that's going to get us the value inside of there. And then we can type .numpy, and then that's going to get us our NumPy array, right? Because that's what we want. And then in order to get just the 51 values, what we can do is a little bit of indexing. So we want all of the values again, and then we want only the 51st. Yeah, that should be about right. Let's take a look at the shape. Yeah, there you go. So what I've gone and done there is first up, we've gone and grabbed the output, specifically the output of our results variable. Remember, you're going to get this over here. So you've got this dictionary, which has output underscore 0. Then we're converting it to a NumPy array using the .numpy method. And then what we're doing here is just some advanced indexing. So we're grabbing all of the values, and this is effectively saying, I want all of this, I want all of the people. And then the last value is basically saying, get me the first 51 values, because those 51 values are going to represent our key points, because that's all we need to render our image. Again, all of this code is going to be available in the description below, so you'll be able to see it. So what we're actually going to do is we're going to apply this transformation here so that we only have our key points with scores. And this is what we're effectively going to need to be able to use our rendering functions from our Movenet Lightning existing code. So let's go on ahead and do this, and we're also going to reshape it a little bit, but you'll see that in a second. Okay, so that is the new code that I've gone and applied. So I've gone and created a new variable called keypoints underscore with underscore scores. And this is going to be the set of values that we're going to be able to use for our rendering. So we're grabbing our results value here, and then all of this code is exactly what we've done here. So that's going to return an array that looks a little bit like this. Let me zoom out so you can see it. So it's effectively just going to be one big array. Now, what these values represent are our y coordinate, our x coordinate, and our score. So our detection confidence. Let's zoom in one more. Now, in order to actually use it inside of our rendering functions, we want to have each key point as its own set of values. So what we can do is type in .reshape, and then we're going to reshape it. So 6 people by 17 key points by 3 values for each key point. So it looks like this. So you can see that we've now got a single array for every single key point. So this is going to be our y value, this is going to be our x value, and this is going to be our score value. Now what we can do, now that we've got it in this shape, that is effectively what we're doing here. So we're storing that value inside of a variable called keypoints underscore with underscore scores. Let's go on ahead and test this out and make sure that all works. So if we go and run this now, should get our pop-up. That's all working well. And you can see down there that we are getting our correct shape, right? So this is in the shape. We've got, let's stop our frame, or let's quit out of that. So you can see that we've got all of our key points. So we've got this showing up. So that is one key point, that is one key point, that is one key point. And this key point, keep in mind, is going to be the nose, and then the left eye, the right eye. So the nose, so this one, the first one is the nose. This is going to be left eye. This is going to be right eye. So they basically follow this pattern here. So nose, left eye, left ear, right ear, left shoulder, right shoulder, so on and so forth. Right. So say, for example, we wanted to, let's get rid of this. We don't need that anymore. So if I typed in key points with scores, if I wanted to, for example, grab the first person, I can type in .0. And so these are the key points for the first person from our detections. So these are our normalized coordinates. And what I mean by normalized is that they are not scaled for the size of our image. So we're going to have to handle that. But our rendering function, I believe, already does that for us. So these are our normalized coordinates. And then this is our how confident our Movenet multi-person model is that those coordinates are correct. So these are effectively how valid the detection actually is. So you can see that some of these are higher. And what you'll actually notice is that these coordinates are higher because they are the ones that are shown on the screen. These are lower because these are the lower body coordinates. Now you can see that I've only got the upper half of my body in the frame, so it's going to have low coordinates for those ones that it can't see. And if you actually take a look, so what's the last value? The last value is the right ankle, the left ankle, right knee, right hip, left hip. It's not going to be able to see that because it's outside of the frame. Hence why you've got these poor coordinate values or these poor confidence metrics for those there. Cool. Now what we can do is we can actually bring in our rendering functions. Now, in order to do this, we're not going to rewrite it all over. We're actually going to use the code that we wrote in the Movenet Lightning tutorial. So this is available through my GitHub account. And if you check the description below, the code will be there. So if you go to github.com/nickknockknack/Movenet Lightning, what you can do is go into one of the Jupyter notebooks. So in this case, this one is called Movenet Refined. They both do the same thing. And down here, I've actually got the code to draw the key points and the code to draw the edges. So we're going to copy the draw key points method and paste it in here. And then we're going to copy the draw edges method as well. So that is down here, or draw connections method. So there's two parts to the draw connections method. There are the edge connections. We're going to grab that. And there is a function called draw connection. So we're going to need that as well. All right, now let's take a look as to what these two functions actually need. So these are only set up to handle one person at the moment. So what we're going to need to do is create a new function that loops through each one of our people detected in the frame and draws those key points. So the first method is draw underscore key points, and that is expecting the frame, so the actual image, the key points for a single person, and then the confidence threshold above which we want to draw. So say, for example, you get low confidence metrics. So say right now we're getting 67, 81, and then 21. So we might actually set a confidence and go, hey, don't draw anything which is below, I don't know, 25 or 30%. So this is what this confidence underscore threshold variable is. And then we've got our second function, which is our draw connections method, which you can see over there. And this takes in one additional value. So it takes in our frame, our key points, our edges, and our confidence threshold. So the frame, the key points, and the confidence threshold are the exact same. The core difference is the edges. So these edges effectively tell us what joint connects to what other joint. So in this case, joint 0 connects to joint 1, which means that our nose connects to our left eye. Let's take a look at our next connection. Our nose connects to our right eye, and so on and so forth. So these basically just tell us how to connect these joints up together. Pretty cool, right? So what we're going to do is we're going to use the draw connections method and the draw key points method to be able to go and render our results. Because right now we're not rendering inside of our code block over here. All we're doing is we're making the detections. So we'll need to write a function which basically loops through each one of the values in our key points with scores variables and then calls these subsequent functions. So the draw key points method and the draw connections method. So let's go on ahead. And if you want to see how these have actually gone and been built up, do check out the Movenet Lightning tutorial. I'll link to that in the description below, so you can check that out as well. Cool. But what we're going to do now is we're going to create a new function to loop through each person detected and render. So let's go on ahead and write this function. So I'm just going to clear the output of this cell. So let's do it. Okay, so that is our drawing function now done. So I've gone and written def loop underscore through underscore people. And then to that, we are passing through, 4 different positional arguments. So first up, what we're going to do is we're going to pass through the frame that we get from over here. We're going to pass through our key points with scores variables that we're getting from over here. We're going to go and pass through our edges, which is this connection map from down there. And then we're going to set our overall confidence threshold. And then what we're basically doing is we're looping through each one of the values within our key points with scores. So for person in key points underscore with underscore scores, because remember, if we take a look at our key points with scores variable, you've actually got 6 people in here, even though some of them might be low scoring, right? So you're actually going to get sets of key points for 6 different people. You're going to get 17 key points per person. And then each key point is going to have 3 values. So the Y value, the X value, and then its confidence metric for that individual key point. So what we're doing is we're looping through each one of these sets of 17 by 3. And then once we've got that, we're effectively calling our 2 rendering functions. So just these 2 functions down here. So draw key points and draw connections. So that is pretty much about it. So we've written defs loop underscore through people, and then we've gone and passed through the different positional arguments. We're then looping through each one of the people inside of key points with scores, and then we're calling draw underscore connections and draw underscore key points to be able to render those to our frame. And this is actually going to draw on our image, right? So you're not going to have to go and save it as a separate variable. It's actually going to render it onto that particular image. So if we go and now apply this function inside of our detection loop, we should actually be able to see some results. So let's actually create another section. So I'm just going to call it render key points. And we can get rid of this print function down here. So loop through people, and then we're just calling this function down here. So loop underscore through underscore people, and then we just need to pass through our values. So we're going to pass through our frame. We're going to pass through key points with scores. We're going to pass through edges, which in this case is a capital. It's in all caps. So we just need to pass through that variable. So edges, and then we can specify our confidence threshold. So what did we say? What was it? Around about 30% seemed to be appropriate. So let's set it to 0.3. And then all things holding equal, if we go and run this now, so inside of our big loop, this should effectively draw our key point. So let's try this out. And remember, I'm only one. All right, cool. That's working already. So you can see it's drawing all of my different key points. I drop this and move back a little. So you can see that's drawing pretty accurately. So if I stand up, pretty cool, right? So I can move my arms. That's rendering pretty well. And you can see it's quite quick as well, right? So that is the cool thing about this model. It actually works relatively quickly. But as of right now, I think we've got a little bit of an issue with the scaling because you can see that the key points are a little bit low. And this is because when we've actually gone and specified our reshaping, we've made it a square instead of keeping the same aspect ratio. If we change this to something which is a little bit closer to the same aspect ratio, so right now our frame, what is it? Frame.shape is 480 by 640, right? So 480 by 640. So it looks like it's about 75%. So remember, one of the longer side needs to be a minimum of 256, right? Which you can see there. So what we can do is if we typed in 256 multiplied by 0.75, so that's about 192, but 192 doesn't quite go into 32. Oh wait, it does. So we can actually make this 192. So 192 by 256, that should ideally get us something which is a bit closer to our proper aspect ratio. So let's try that. Hold on, 256 multiplied by 0.75. Let's make sure I got that right. Okay, let's try that out. So ideally what we're going to do now is reshape it into an aspect ratio which more closely mimics what we're actually getting from our webcam. So if we try running this now, should be a little bit better. And sometimes when you run the code, you'll get this little gray pop up and then it'll close back down. If you get that, just run it again. So I'm going to run it again. Okay, that's way better. And you can see our rendering is way more accurate. So right now we've got our the key points are actually drawing on my eyes. It's actually drawing on my ears. Shoulders look pretty good. How do arms look? That all looks pretty good. All right, so that's way more accurate. It's pretty much exactly on my key points, rendering pretty quick. Do some squats, yeah. This is how I test out all my models, guys. But you can see that's working pretty well now, right? We're pretty happy with that. That's actually working reasonably well. But right now we've only done it on I don't know, I'm always enthralled by this. This is pretty much what I do in my day job, guys. Just make key point models. All right, cool. That's enough messing around. So Rod, if you did have this during swim training, this would have come in handy because if my arm was straight, it's not tic-tac-tee. If my arm was straight, you would have been able to see that I am, or I do have straight arms. Anyway, regardless. What are we doing now? So we've gone and done it on our webcam, but I've only got one person at the home at the moment, so it's only going to draw one person. But what we can do is we can actually test this out on videos instead. So if I quit out of this, I've actually got some videos inside of the same repository that my Jupyter Notebook is in. So let me show you that. I recorded this video yesterday, and as part of the tutorial going from here on out, I used footage of a Wimbledon tennis match to show the speed and accuracy. And that footage featured Djokovic and was obviously from the Wimbledon site. And this entire video got flagged for copyright violations. So what I ended up doing was drinking a couple of beers and wallowing in my sorrows. Then I woke up this morning and decided that, hey, let's re-record it with some stock footage. So here it is. Alrighty, so picking up from where we left off. So as I was saying in that cutscene, basically what ended up happening was I downloaded some sports videos, which must have featured copyright content, and that wasn't allowed based on YouTube's policy. So rather than sticking with simply using the video capture device, so specifically our webcam, let's go on ahead and use some stock footage. Now, this could just as easily be done with sports analytics footage or footage from that you've recorded yourself or footage that you've gone and collected from somewhere, just be sure to not try to upload it to YouTube. All right, besides the point, let's go on ahead and use a video. So the cool thing about this is that it's really easy to transition from using a real-time webcam to a video. All you need to do is change the value that's passed to the video capture device. So say, for example, we wanted to do this. All we need to do is go and grab a video. So in this case, I got a bunch of videos inside of the same folder that my Jupyter notebook is in. So let me show you that. So I've got a bunch of videos there. So this is the offender that caused me so much drama yesterday. But we've got some additional ones as well. So we've got this footage of people running. So let's actually play these. Make this smaller. So this is the footage of people running. Right, so we can actually use our multi-person Movenet model to track this. Also got one of people playing some soccer. This is probably better because it's got multiple people. So this will be interesting to see how that actually performs. And last but not least, I've got another tennis one. So you can see that there. So we can use each one of these as part of our multi-pose Movenet model, which is exactly what we're going to do. So if I close that down, the only thing that you really need to do is pass through the name of the video to your video capture device and you'll be able to run this on video. So say, for example, we wanted to run it on, let me open that back up, on this running video first up. Well, let's actually do tennis first up. So tennis, so the file name is tennis and then .mp4. So all we need to do is replace this with tennis.mp4. And if I go and run this, you can see that we've got our Movenet model. Now, it kind of looks like our scaling isn't quite right. So you can see that right over there, it's not exactly getting that perfect, but it is tracking a single person. It doesn't look like it's picking up our second person, but we can tweak that a little bit. So what we can do is first up, let's actually drop the confidence threshold to see if we're able to pick up the second person. So rather than leaving it, let's actually take a look at our results. So what are we getting? So we're getting around about 20%. So let's actually drop this to, I don't know, 15% and see if we get the second person. Okay, so we're kind of getting some second person detections there, but it's not that great. Let's actually drop it a little bit lower. Let's drop it to 10. All right, so we've got the second person, but again, these are kind of skewed. And in this particular case, it's kind of blurry, so it's not picking up that second person all that well. Perfectly fine. What we can do is we should first up rescale these key points because right now they're not perfectly scaled, as you can see on the guy over here. You can see that those eye key points are a little bit low. We can fix that relatively easily. So let's close this down. And we just need to close out our capture device. So cap.release CV2. Let me bring that up a little bit. So if it stays open, what you can do is just run this to close it. So cap.release and cv2.destroy all windows. And that is now closed. Okay, but what we've got is a image which isn't in the right dimension. So if we take a look at our frame, do we have anything there? We don't. Let's just run this again. Third time's charm. All right, cool. Let's quit out of that so we get our frame details. All right, so if we take a look at our frame shape, so our frame shape is 1080 by 1920. So right now, the scaling factor that we used for our original webcam probably isn't all that accurate. So it's 192 by 256. If we look at this aspect ratio, so remember the longer side of the video needs to be a minimum of 256 pixels, and both values need to be a multiple of 32. So if we do 1920 divided by 32, so that fits in perfectly. So what we can do is just scale that down. So if we did it divided by 3, we can make the longer dimension 640. And if we did 1080 divided by 32, okay, so that's a little bit close. So if we divide that by 3, we've got about 360. But that's not going to fit into 32. So 1080 divided by 32 is 33.75. What am I doing? So let's work out the aspect ratio. So 1920 divided by 1080 divided by 1920. So what I'm trying to do here is just get a similar aspect ratio to what the existing image has. So it looks like it's about 0.5625, right? So what we can do is multiply 0.5625 by 640. So which is 360. How did we do this again? So that is not going to work through. So 360 divided by 32. All right, there we go. So 11.25. So this is close. Now, what we can actually do is we can either scale down or we can scale up. So in this case, it's probably closer to scale down. So we can do 32 multiplied by 12 or 11, which will be 352 pixels. So we'll make this 352. And let's try that again and see what our scaling looks like. All right, that looks way better already. So you can see it's grabbing our second person. The key points look a lot more accurate. And that is it there, guys. So you can see that that is tracking us 2 people. Got some weird detections over here and over here, but that's fine. Pretty cool, right? So you can see the impact of changing our scaling, right? It obviously performs a lot better. We can close out of this. Let's actually try using a different image or a different video. So rather than using tennis, let's actually try the soccer one. So that's with our soccer images. And I think the soccer video is the same shape. So that's why we don't need to adjust our scaling. We're getting these weird detections over here. So we might be able to increase that confidence threshold. Let's quit out of that one. Let's set our confidence back up to, I don't know, 30%. So in order to change our confidence, all we need to do is change the confidence metric that we pass to our loop _through_peoples function. So we can do that there. And let's just double check that our shape is the same for our soccer video. Yeah, it is. So it's 1080 by 1920. So we don't need to change our scaling there anymore. But again, so what you're trying to do when you're changing this scaling is the longer side needs to be greater than 256 and divisible by 32, and the shorter side just needs to be divisible by 32. But you want to keep the aspect ratio or the ratio between these two values as close as possible to make sure that you're not getting any weird scaling. So what do we do there? We boosted our confidence metric. So let's go run this again. All right, that looks way better. We're not getting these weird detections out here. And we're picking up our second person as he runs into score. Look at that. That's actually working really, really well. Oh, and look, it's even picking up that second guy over here. Pretty cool, right? What is our last video? So we've now gone through our tennis video and you saw that was detecting reasonably well. We've now gone through our soccer video that was detecting pretty well. And again, you could do this on real-time soccer footage as well, or like actual games. What was our last one? I think our last one was running. So the last video that we had was called running. And if you want to try these videos, you can actually grab them from this site. Again, this is completely unsponsored. I was just scrambling to find some footage I could use this morning. So if you take a look at mixkit.co, there's a bunch of videos that you can take a look at. So I think I downloaded this one down here. So soccer players playing on field, and then I grabbed one for running and one for tennis as well. So let's try the running one. So remember, the name of the file for running is called running.mp4. So if we go and try that out, got our pop-up. Look at that. Perfect. And so the video itself is a slow motion video. So again, it's not the actual model running slow. It's just the actual video is slow, is sort of like slowed down. So just keep that in mind. This will run perfectly well on fast video as well. But on that note, that is our 3 different videos. Now, again, if you wanted to go back and use it on your real-time webcam, all you need to do is change this to the number of your video capture device. Remember, you'd have to change your scaling back as well. So what was it for our webcam? So I think it was our webcam dimensions are 640 by 480. 640 divided by 32 is perfectly fine. So we can do 640 divided by 3, maybe. 4. What do we have? We had 256. 480 divided by 640 is 0.75. So 640. So if we just did 256, which is our minimum, multiplied by 0.75. All right, so it's going to be, so again, if you wanted to go back to your webcam, you just need to ideally maintain the same aspect ratio. So if we made this 256 and this 192, and remember, I've changed the video capture device over here. So if we go take a look at our webcam now, You can see running perfectly fine. It's got me, and again, you can see that it is very fast. So it is actively tracking me. That is me moving my body really, really quickly. Pretty cool, right? And on that note, that does wrap it up. So we've gone through a bunch of stuff, and thanks again for sticking around, even though we had to transition to a new set of data or new set of videos. So what we did is we first up installed and imported our dependencies. We then went and loaded our model. And remember, we loaded this from the Tensorflow Model Hub. We then made a bunch of detections. And remember, key thing is key tweaks you can make are to tune your confidence metric and then make sure that you're passing through the correct aspect ratio. Now, the larger image that you pass through, the slower your detections are going to be, but also you're likely to get a performance boost. So ideally get better detections in that particular case. And what we also did was we also used our draw key points method, our edges, and our draw connections method from the existing Movenet tutorial. Thanks again for tuning in, guys. That about wraps it up. Thanks so much for tuning in, guys. Hopefully you enjoyed this video. If you did, be sure to give me a big thumbs up, hit subscribe, and tick that bell. Thanks again for tuning in, guys. Peace.